Okay, this is lecture 45. I'm going to discuss how to find the stochastic differential equation for a two-state problem. Okay, so remember this is what we had last time for a stochastic differential equation. We had this typical form here where we had dx is equal to some mu, which is our expected value, plus our covariance times this our Wiener process, and the terms are given by these equations here. So our b is v to the 1/2, where v here is our covariance, or our approximated covariance. Okay, so we're going to consider this two-state problem. So here we have two states, S1 and S2. We have 8 different transitions. So remember what I said last time, you actually want to put this in a table form in order to try to come up with what the SDE should be. So here's our potential transactions, and so here typically we think about one person moving from each category, but this is just generic. So so here our transition 1 would be if we lose lambda 1 from our S1 category, and so this is the probability of doing that. Our 2 is if we gain some number lambda 1. Here, if our third transition is we're losing lambda 2, fourth is we're gaining lambda 2, fifth is we move from S1 to S2, so we lose 1 in S1, gain 1 in S2. Our sixth, we lose 1 in S2, gain 1 in S1. Seventh here is when we're losing 1 in both, or in 8 is when we're gaining 1 in both. And then we call our transition 9 where nothing happens, which is 1 minus the probability of all of our previous transactions. Okay, so if we were looking for the expected change, here's the table that we had on the previous slide. So for finding the expected change, remember what you do is you take your probability and you multiply it by your change. So here our probability for our first one is D1. We're just going to simplify this to D1. So our probability is D1 times our change, so our times our minus lambda 1, 0, plus B1 times lambda 1, 0, plus D2 times minus lambda 2, plus B2 delta t times lambda 2, 0 lambda 2, and then M1, 2 times this, times delta t times the matrix, the vector negative lambda 1, lambda 2. Then we have our M21 delta t times this vector lambda 1 minus lambda 2, plus M11 delta t times this vector minus lambda 1 minus lambda 2. And then we have our M22 times the vector lambda 1 lambda 2, and then 0 times 1 minus the sum of all of those. So if we simplify this, this is what we had on the previous one. If we simplify this, then we basically have in our first column we have minus D1 lambda 1 plus lambda 1 B1. We don't get any from these. We have minus lambda 1 M12, and then we have M21 times lambda 1 minus lambda 1 M11 and plus lambda 1 M22, and all of this is times delta t. In the second one, everything is multiplied by lambda 2, so here we have a 0, 0. Here we have a minus D2 delta t plus B2 delta t, M12 delta t times the lambda 2, M21 delta t times the minus lambda 2, M11 times the minus lambda 2, and M22 times the lambda 2. And then this gives us nothing. So looking at that, to get our mu term for our stochastic differential equation, we just take this and divide it by the delta t, so we really are just left with this vector here. Okay, our covariance, remember we estimate our covariance by E delta S transpose. So here we have those same transactions, just what we have now is we have the vector times the vector transpose. So this is going to end up giving us a matrix. So all of these look the same as before, except for now we have the vector times its transpose. So when we do this multiplication here, we have these matrices that we get. Some of the matrices have a lot of zeros, and some of them actually are non-zero, but they're symmetric. So we combine them all together, and we get this matrix, this 2 by 2 matrix. And here, all of our first terms are multiplied by lambda 1 squared. And then we have these lambda 1, lambda 2 terms, and then the lambda 2 squared terms. So our differential equation for a two-state problem, so we have our ds is equal to our mu times our dt plus our b times our dw. Here we had our mu that we found, and our b is actually v to the 1/2, where we found the v to be this matrix. So in the numerical algorithm, we actually are going to be able to just use this v to the 1/2 and multiply it by a vector. If we want to, we don't have to necessarily put it into different terms, but there's lots of times people need to find various ways of finding the square root of a matrix, or matrix raised to the 1/2 power, because this isn't necessarily an easy task. If it's a 2 by 2 matrix and it's positive definite, which is definitely what we have, then it's a little bit easier and we can just use this formula. If v is larger, then there's alternatives for calculating v to the 1/2, but we're not actually going to cover those methods in this course. Any good numerical linear algebra book can give you good ways of calculating v to the 1/2. And for our purposes, I believe the only problem you probably will encounter, which you're going to need to calculate v to the 1/2, is the third model on your project 2, in which you're going to have a 3 by 3 system, and so that one, but you should be able to just use the built-in MATLAB code of v to the 1/2. Okay, so next time we're actually going to talk about these numerical solutions and how you actually come up with a numerical solution of a stochastic differential equation.